In this video, I want to talk about representing integers in binary as well as 2's complement. So in this table, I have some decimal numbers and their binary representations. And this is a 3-bit system, which simply means that all the binary numbers are 3 digits long. So note that for an n-bit system, that system can represent up to 2 to the n values. So in this case, we have 3 bits. So it can represent 2 to the 3 values, or 8 values, so from 0 to 7. And for 15122, for C0, integers are 32 bits long. So in that case, we can represent 2 to the 32 values. So one issue with this table here is that there are no negative numbers. So if we want to represent negative numbers, we have to represent the decimal numbers in a slightly different way. So in order to represent negative numbers in binary, we can use a system called 2's complement. So first of all, let's think that we have a positive integer x, and we know its binary representation. And we want to find the binary representation of negative x. Well, we know that x plus negative x should equal 0. And we can use this fact to find the binary representation of negative x. So if we have 1, for instance, its binary representation is 0, 0, 1. So we want to find the binary representation of negative 1. Well, if we know that 1, 1, 1, if we add the numbers together, it'll actually equal this number. And since it's a 3-bit system, we can just get rid of the 4th bit. So we see that 1, 1, 1 plus 1 is equal to 0. And therefore, we know that 1, 1, 1 is equal to negative 1. Similarly, let's look at 2. Let me just get rid of this. So 2 is 0, 1, 1, 0, 1, 0. And we see that if we add it with 1, 1, 0, we again get this number. And therefore 1, 1, 0 is negative 2. So we can continue filling in the table. This will be 3, and this turns out to be negative 3. And this turns out to be negative 4. And this is still 0. So this is how 2's complement represents negative numbers. And we can actually see that for 2's complement, in order to get the negative value of a positive number, we can simply flip the bits and add 1. So if we have a positive number 1, which is 0, 0, 1, in order to get negative 1, we can flip its bits. So flip its bits. So instead of 0, 0, 1, it's 1, 1, 0, and then add 1. So this is equal to 1, 1, 1. So we know this binary representation is negative 1, and this binary representation is 1. Also note that for 2's complement, the minimum integer is equal to negative 2 to the k minus 1, where k is the number of bits. So for our 3-bit system, the minimum integer that can be represented is negative 4. And then for the maximum integer, it's 2 to the k minus 1 minus 1. So for a 3-bit system, the maximum positive integer that can be represented is 3. So now that we know how to represent negative numbers in binary, I want to talk a little bit about integer overflow. So let's say we want to add the numbers 1 and 3 in our 3-bit system. Well, we know it's equal to 4. However, we can only represent up to positive 3. So what happens when we add the binary representations together? Well, it'll be equal to 1, 0, 0, 0. So it'll actually be equal to -4 for 2's complement. So essentially, we overflowed past the maximum positive number into the minimum negative number. And if we did a similar thing for 2 and 3, instead of 5, we would actually overflow to -3. Because instead of going 2, 3, 4, 5, we go 2, 3, -4, -3. And similarly, for integer underflow, if we add -2 and -3, we get -5. However, we can only go to -4. So if we add these together again, we see that we can get rid of the last bit. So adding -2 and -3 gives us 0, 1, 1, which will end up giving us 3. So instead of going -3, -4, -5, we underflowed to the maximum positive integer, so it went -3, -4, and then 3. So because of integer underflow and overflow, we can actually think of 2's complement as kind of a circle. So for our 3-bit system, as we continue going up, 0, 1, 2, 3, 3 is the maximum positive integer. So if we add one more, it'll go to -4. And we can keep adding -4, -3, and continue. And if we keep subtracting -2, -3, -4, we subtract one more, it'll end up equaling to +3. And this is a example of 4-bit system, which represents up to from -8 to 7. So if we keep adding, if we add to +7, it'll end up overflowing to -8. And similarly, if we subtract from -8, we'll get to +7. Finally, I want to talk a little bit about multiplication and division for 2's complement. So again, -2 times -3 is 6, which is too large for our 3-bit system. And if we end up multiplying their binary representations, we end up getting a number such as like this. And again, we can cut off the extra bits. 110, so that'll be equal to -2, which makes sense since it goes 2, 3, instead of going 4, 5, 6, it'll go 3, -4, -3, -2. So this actually turns into -2. And just an extra note for division, we want to make sure that for C0, we don't want to divide by 0, or we don't want to divide the minimum integer by -1, because that will cause a arithmetic error for C0.